Okay, I couldn't sleep last night because I had to prepare for slides today, apparently. So I'm kind of completely caffeinated. I was drinking a few cups of coffee almost for last 24 hours or so. So I'm not in my, I'm kind of out of my mind now. So I was thinking what to talk about, but then I decided to talk about something that I'm thinking like once or twice, almost every year for last 10 years or so. But then I thought maybe it's too much details I might be giving you today. So instead of doing that, let me just go over some basic ideas and give you a story, what I have been doing sort of for past 10 years or so. And then I'm going to briefly summarize what I did for last a couple of years or so. But then probably for some of the experts in the audience, you may not be satisfied, but you can always talk to me. But today, I'm going to just give you a story. So before I begin, how many of you can recognize this number, 211, right? I mean, 200 or 210. Probably this doesn't mean much, yes? 211 physics courses?
Yes.
No. How about this one? How about this one? Come on, someone should recognize. This was actually the number of sunny days in each city. And I spent 1 year in Pittsburgh, and I was very happy in the summer, August. But then starting October and November, basically there was no sun until spring. It's very unfortunate. Actually, it was very cloudy. And then someone told me that Pittsburgh was the second cloudiest city in the United States after Seattle. So I was very surprised, but physics-wise, it was great. Only weather-wise, it was very cloudy. Okay, so like I said, I'm going to give you sort of a story rather than giving you some details. But you can always ask me, interrupt me. As you know, even if you are not a high-energy physicist, so we all heard about discovery Higgs. And we know that this Nobel Prize was awarded a few years ago. But then we know that actually, although 2 people received the Nobel Prize, but we know actually the Nobel Prize should have gone to whole experimental collaboration, both Atlas and then same as experimentalists. And then we have our colleague sitting in the audience. Now, the thing is, discovery of Higgs boson, of course, was a very impressive experimental achievement. But unfortunately, so far, all the properties of this particle were actually following textbook predictions. So no significant deviation beyond whatever standard model is predicting. But nevertheless, we know there's just something missing in the standard model. Hopefully, that gives us some hint toward the beyond standard model. So the game is taking lots of pictures. I hear like 40 million pictures per second. Then each picture has roughly more than 100 megapixels. And they're taking this picture for next 10, 20 years. And hopefully writing down more terms beyond this Lagrangian of the standard model. So then at some point, we like to discover something. Then experimentalists will shout, we found something, right? So then the question is, what is that something? And how hard is it to identify what was actually found, assuming there is something? So then how do we know what we see is what we are actually looking for? Suppose we found a new particle. So then, of course, we have many questions. First question might be, how is it produced? It's from proton-proton collision. But internally, is it quark-antiquark annihilation? Is it quark-quark annihilation or quark-glue annihilations? How is it produced? How does this particle decay? Well, probably we have some idea what this guy might be by just finding this particle. But is it a fermion? Is it a boson? How does it interact with the rest of the standard model particles? But nevertheless, among these many questions, very first question might be, how heavy is it? Right? What is the mass of this new particle? So why do we care about the masses? Of course, this mass is actually a common parameter in our Lagrangian and Hamiltonian. And often this mass information gives us some information about theory. For instance, here is a couple of examples. So if we know about some mass scales, sometimes that can give us some hints. What would be the size of the extra dimensions, for instance? Or sometimes this mass information can give us what would be the symmetry breaking scale associated with the particular model. In this case, I'm referring to some kind of supersymmetric model. And sometimes, by measuring the masses, sometimes we can get an indirect constraint on the masses of the particles that we are looking for. For instance, before Higgs topology was discovered in 1995, I believe, then people knew about the existence of W and then Z, and then people measured the masses of these two particles. That gives indirect constraint on the topology masses that people are looking for at that time. However, the reason why this is not actually extremely powerful is actually there are a lot of uncertainties going into this estimation, so it is actually indirect. But nevertheless, that can give us some information. Similarly, after topology discovery, the masses of these three particles can give us some hints on the mass of the Higgs particle, and the people knew a lot about the Higgs before it was discovered. Once again, this is only indirect. But at the end, this measuring the masses, mass information actually helps to expedite that discovery by making an optimal selection. So how do we measure the masses at the LHC? Well, the one way, easiest way to measure the mass is to combine the two visible particles, calculate the total mass energy of the two visible systems. In this example, this is a very old plot now. So I'm looking at this mu plus mu minus system, and then find the energy and measure energy and momentum, construct the so-called invariant mass of the two particles, and then plot how many events we observe as a function of the dead quantity. So then we see that generally this one actually falls down. Remember, this is log versus log. And generally, this guy falls down. But then occasionally, we see this little peak here. The location of this peak corresponds to actually certain particles. So in all of these particles shown in this plot are actually the composite particles, which are made of the quark and the antiquarks. But then the Z is supposedly a fundamental particle. Then we know this guy is at the 91 GeV. We hope to find something more beyond this 90 GeV or so. But then many of you recognize this is almost exactly actually the same as a harmonic oscillator. So when you actually push this swing, the child is sitting on a swing. So now I have enough experience because I have 3 children. So you don't want to push, when the swing is coming toward you, you don't want to push swing, right? You have to actually follow this natural frequency so that you can minimize your force, you give the large amplitude. You don't want to go backward. So the thing is here, the F0 denotes the natural frequency of a certain harmonic oscillator, for instance, damped or forced harmonic oscillator. So this one, remember the E equal to mc squared, and E is also equal to HF. So this frequency actually is related to the mass of the particle. And this y-axis is amplitude when you actually have this harmonic oscillator. But that is somehow related to probability, or that also gives you some information about strength of the interaction. So then this x-axis here is a driving frequency that you can negotiate with how much energy actually you provide. So then this frequency is actually close to this natural frequency of the harmonic oscillator. You see this kind of resonance effect. And how wide this resonance is, how tall this resonance is, that has something to do with the property of the particle. The width of this resonance is actually related to how long this particle lives at the LHC experiment. So this is another example, the Higgs, and there's a little bump. And this location was around 125 GeV. This is a total invariant mass of the 2-photon system. So you measure the energy momentum of the 2 photons and then calculate total energy in the center of mass frame. And then you see this nice peak. And then you can do the statistical analysis, how significant it is to find this particle at 125 GeV or so. And then by measuring lots of other properties, we know how this particle is produced, how this particle decays, what is the theory that goes in this triangle diagrams. So we learn a lot about the Higgses. But then we need to calculate the total energy, right, to find the mass, to find the peak, and then interpret the peak as a particle that has a mass, certain width. But then we need to calculate the mass, total energy. So then what if there is a missing particle in the finite state? Well, we are missing something, so which means most likely we are not going to measure energy or momentum of the missing particle. So then what can we do in that case? Here is an example. Here is a W particle decaying to lepton and then neutrino. So electron we can measure experimentally, but neutrino it actually rarely, it doesn't interact with the detector, so it escapes. which means that this guy is not actually reconstructed. However, assuming W is produced with all the visible particles, and then W decays into electron and then neutrino, we can actually constrain. This is not actually not observed, but that doesn't mean the W mass is unconstrained. For instance, let's assume this direction is the Z direction. So the proton, one proton is coming in the Z direction, and the other proton is going in the opposite direction. So collision occurred somewhere here in the middle. And we know that actually proton has very little transverse momentum. So we can assume that the two proton system, initial system, effectively actually there is no net transverse momentum, meaning that if this guy takes away certain momentum on the transverse plane, assuming W is produced singly for now, so then neutrino should take actually carry out some momentum to balance the total transverse momentum on this red plane. So that way we can calculate the mass. However, we don't know the Z momentum because we don't measure actually the individual momentum of the two partons colliding along the Z direction. But we can get some constraint on the transverse momentum of the missing particle using energy momentum conservation. So historically, the solution is called the transverse mass. So here ME refers to the mass of the electron. Here M nu is the mass of the neutrino. They are almost massless. So practically, I'm going to ignore them. But nevertheless, they exist here. Mathematically, they exist. And then this guy, EE, is called transverse energy of electron. E nu is the transverse energy of a neutrino system. And then this guy refers to transverse momentum of a neutrino and an electron. So transverse energy is defined by this equation. Basically, I'm ignoring the Z component of the momentum here, Z component of the momentum here, taking the transverse momentum to calculate the two energies. Then let's compare this so-called transverse mass against four-dimensional mass. When you calculate four-dimensional mass, so this is what you get. Once again, sorry, maybe I switched the notation here. So one visible particle, invisible particle, and the EA, EB are the transverse energy of the two particles in the final state, electron and neutrino. And then these guys are momentum product of the two transverse quantities. And then this cosine hyperbolic function, and then the eta is the basically the measure of the polar angle in a different frame. And the transverse mass is defined here, but invariant mass is defined with this cosine hyperbolic functions. But we know the cosine hyperbolic function is always greater than 1. Therefore, transverse mass should be always less than this four-dimensional mass, 1 plus three-dimensional mass. So there is an inequality over here. And the equality is actually achieved when delta is equal to 0, meaning that electron and then a missing neutrino have actually the same rapidity. Then actually the equality sign is achieved. I made a note here. This is not the same as the drawing with zero information. This is actually the result of the something called sophisticated minimization procedure. So using this one, we can actually calculate the mass bounds in the W, mass bounds on the W in the leptonic chain when W decays semi-invisibly. So this transverse mass is always less than mass of the decaying particle, in this case W. So then we expect to see some kind of drop over here. This is called the endpoints. If we are able to measure these endpoints, we can set the limit on the mass of the W, which is a decaying particle. Yeah, here, yes.
Endpoints are always at the where the Z momentum is 0, right?
No. Actually, neutrino can have Z momentum.
Yes,
but the
Z momentum is 0. Isn't that the case? I thought you just said that the transverse mass equals the mass when the
transverse mass.
Mass when
This equality is satisfied when delta eta equal to 0.
Yes. So that's that hard line is when delta eta equals 0.
I mean, it is obvious, right? I mean, when you compare this one, when this guy is equal to 1, transverse mass is equal to four-dimensional mass. So when you say the Z momentum, are you referring to Z momentum of the electron or Z momentum of the W system?
Let's go on.
Z momentum of the
Four angles are the same.
Yeah.
Z momentum of the W.
Correct, yeah.
Z momentum of the W. No, I mean Z momentum doesn't have to be zero. You can have if this is a singly produced, then probably there might be an ISR. So W can be boosted in some direction against the ISR. Okay, so in this case, I ignore the now the electron mass and the neutrino mass. So this is transverse energy of the electron, transverse energy of the neutrino, and then this will give us the product of the two transverse momentum. So we expect to see some kind of big drop around 80 GeV, since W mass is 80 GeV. However, because of the finite detector resolution and then due to the finite width effect, actually there is a long tail beyond 80 GeV or so. But nevertheless, we see there is some correlation with the location of the peak here with the mass of the decaying particle. Now, the question is, what if there is more than one missing particle? So the next simplistic case will be, of course, two missing particles in the final state. Surprisingly, this is actually a very hard question, at least 15, 20 years ago. But now we know a lot about this system, but it's not that easy system. So because of the, this is a rather complicated, there are many approaches to this problem, and there are many solutions. I'm just showing a few list here. So depending on how many assumptions you put in your calculation, there are actually many different ways of tackling these problems with the two missing particles in the final state. If you have a very few assumptions, you can measure something called the missing transverse momentum. That's the simplest quantity that you can measure, experimentally challenging. But for this particular case, this is the simplest quantity you can make. And then if you have a lot of assumptions, for instance, you can use all the information about the dynamics and the kinematics in your model. Then you can use something called the matrix element method. But nothing can compete against this matrix element method if you have this thing. However, that actually requires a lot of assumptions. So depending on how much assumptions that you put in, you can appropriately choose what you want to do. But then, because this method down here actually assumes a lot of different things, you can actually draw very specific conclusions. But on the other hand, the method over here actually depends on the less number of assumptions. You may actually draw very vague conclusions. But because of exactly the same reason, you can get actually, I would rather say these methods are very robust because it requires a less number of assumptions. But the method down here actually are fragile in a sense that they depend on the lots of assumptions. So if you make one assumption or two assumptions, you may get different answers. So in that sense, these methods are not actually very robust. So at the end of the day, depending on what you want to achieve, probably you want to make a certain balance here, right? So what happens is that for a given topology that you like to study, so we always impose certain interpretations and try to design a suitable variable to understand that particular topology. That's what has been done historically. So what is a good variable? What is a good method? So this is a number of event or amplitude or probability. And suppose this is the some kind of function that we are interested in to measure, in this case mass, for instance. So then as we saw earlier, this kind of a delta function might be the ideal case, but we never observed such a case. But this resonance with some width, finite width, this is just perfect. This is probably as much as we can get here, right? It cannot be better than this one. But this kind of structure also works fine. And then this kind of distribution actually appears in a particular topology called the Antidote topology. One decaying to two particles, each one decays into two again. So it looks like a antler shape. The example that I'm going to discuss is actually corresponds to this example. Just like a single production of the W decaying leptonically. But missing ET or HT, some other method are actually up in the list, actually give very broad distributions, meaning that we will not be able to draw some mass information out of it. we might actually be able to use to discover something, but that doesn't mean we will be able to draw some mass information out of those variables. Well, there are many complicated topologies that appear in the BSM models, but some of them are simple, but some of them are rather complicated. Most of these actually the topology have been actually studied in detail. So I'm not going to describe, but I'm just showing you the people have thought about many different topologies. So as I said, there are many ideas, many variables, many methods, many different algorithms, computer code. So depending on what kind of topologies actually people consider. I cannot show you everything, but just a list of a few things, depending on how optimistic you are concerning the missing transverse momentum reconstruction. So for instance, if you actually are trying to guess the momentum of all the missing particles in the final state, maybe you are in the optimistic side, then you might be able to choose a certain method to do something useful. But all these problems have some advantages and disadvantages. So what I'm going to do is I'm going to focus on one of the many boxes over here, mostly this box over here. But interestingly, the other guys are sort of related to each other. So I call these guys as cousins to each other. So, but nevertheless, I'm going to focus on this one for a while. So story begins about 20 years ago now. This graduate student in Atlas collaboration, didn't have anything else to do because there was no data, right? So he thought about some kinematics problem. He wrote a paper with a postdoc, David Summers, 20 years ago. So what they were doing was, as I said, they were considering two missing particles in the final state. So they chose one of the supersymmetric points. So here the two model particles are produced from the PP collision. And each model particle decays into one visible particle, one invisible particle. So there are two missing particles. So the question is, how do we measure the masses of the mother or daughter particle, invisible particle? So that is the actual question. So they have written a paper. I will describe what they have done later. And then, since then, this method is known as Cambridge MT2. So here, 2 stands for two missing particles. T stands for transverse. M stands for mass. And then 4 years later, these two guys, I believe Phil Stevens was also postdoc at that time. I couldn't find the picture. Ellen Bauer actually joined Cambridge, while the Chris Lester was still a graduate student. So these two, I believe, he was a postdoc. I think he was a postdoc too. So they revisited this idea, and they actually studied a little bit more, and they found a lot of interesting mathematical properties. And they wrote a paper. It's not uncommon to include the pictures of authors in the paper, but it was not, it's not uncommon, but it was very interesting to see the pictures. This is actually their archive paper. Of course, I don't think journal allows to include the pictures of the authors in the paper. And the title was actually very fancy. And then if you search, actually this is the only paper that has a glamour in the title, if you search Inspire. But I think I heard from Chris, this was published in Journal of Physics or some European journal. So editor didn't like the title, so they actually had to change to this one. But they sort of negotiated. They kept this second part there, but they nevertheless, they included it. So like I said, the one difference between the first and second paper is second paper, they use the same method, the same idea that I will describe, but they just elaborated a little bit with the more mathematical properties of this method. Since then, this is what is known as Oxbridge MT2, because Ellen Bauer became a faculty at Oxford, Chris Lester became a faculty in Cambridge. I lost keeping track of him, but he's there in the field, but I'm not sure where he is. So here, okay, so let's quickly recap. W mass, single production of W. The only missing particle is actually the neutrino, which decayed from W, and we can form something called the transverse mass, and then plot number of events as a function of this mass. Then we see the location of peak is correlated with the mass of the decaying particle. Now, if you have two missing particles in the final state, so here the two model particles are some hypothetical particle called the partner of the lepton, called the supersymmetric lepton, and then this particle decays into lepton and some missing particle called the neutralino. So two particles are produced, and each one decays into one visible, one invisible particle. And here, as we know here, right, we have one missing particle here, another one here, and then P1, P2 refers to the momentum of the two visible particles. So since we have two missing particles, right, here and then here, we can actually form two transverse masses. So each one can be calculated this way, assuming we know the transverse momentum of the individual missing particle. So now we have two of those two. Since each one is bounded above by the mass of the mother particle, decaying particle, as I said earlier, if I take the maximum of those two, it's still bounded above by the mass of the mother particle. So maximum is actually a little bit better because you can get a sharper endpoint. But minimum also works, but maximum is better. But the problem is we don't know the individual transverse momentum of the missing particle. Because previous example, single production case, there was only one missing particle. So we can use energy momentum conservation, figure out the transverse component of the missing particle. In this case, there are two missing particles. So we can use energy momentum conservation, but we don't know how the splitting actually occurs between the two missing particles. So the best that we can say about this situation is the minimum of that quantity over this constraint still satisfies this mass constraint. And then since we have two missing particles, so these authors decided to include two at the end of M2. That is what is known as MT2. So then it looks like a numerical recipe. It is actually a numerical recipe because these quantities are well defined, but you have to minimize over the constraint to calculate this MT2 quantity. So in their first couple of papers, they showed actually that if you input the mass of the missing particles correctly here, so then there isn't clear endpoints which corresponds to the mass of the mother particle, mass of the decaying particle. So the benchmark point they chosen actually corresponds to the input message over here and then output message over here. So at least this one requires a lot of statistics, but nevertheless, this works in principle. So then, as I said, we need to input mass of the missing particle here, assuming we know this value. But a priori, we don't know the mass of the missing particle. In that case, we might as well actually vary mass of the missing particle, and we call this one as a test mass or a trial mass. So if we change the mass of the missing particle away from the true value, then corresponding endpoints also get shifted. But of course, we don't know. But this distance, roughly, there is a formula between the two, but also shape gets modified slightly due to the sum of the dynamics involved in the production and the decay. So at the end of the day, what happens is that these endpoints of this distribution is obtained for a given test mass. If test mass happen to be same as the mass of the daughter particle, then corresponding endpoints actually give the correct mass of the mother particle. So at the end, this variable gives one-dimensional constraint between the two masses involved in this decay. So in 2006, so when I was about 11 years ago, so I was about to finish my degree and then moving to Fermi Lab for my first postdoc. And then I got the job, so I wanted to work on something different. So I decided to look at this MT2 because this was very interesting, but the authors actually repeatedly claimed that they were not able to find analytic solution to this numerical recipe. So I'm a theorist after all. So I was very curious why they were not able to find an analytical expression, and then they kept this numerical recipe. But then I look at actually citations, right? After first paper, almost 5 years, they got basically 0 citations within fluctuation, right? But then suddenly, around 2006, they started actually getting tons of citations. By the way, this is not the sum. This is per year, right? So 2016 over here, still it's growing every year. So then summer, like I said, I didn't have anything better to do, so I look at this revisited. But I'm a theorist, once again, right? I have to simplify the situation. So I assume that, so some of you know the sum, what is the ISR? So I simplify the case. Only the two W's are produced, nothing else. And each W decays leptonically. So 2 visible particles, 2 leptons, and then 2 neutrinos in the finite state. Nothing else. In perfect resolution, ideal situation. So W's are produced back to back. Completely ideal situation. And the missing it is perfectly well measured. So the visible momentum of the visible sector actually is balanced against the momentum of the invisible particles. They are back to back. And then visible will be, momentum will be sum of the 2 vectors, electron, maybe another electron. And then 2 neutrinos, sum of the 2 missing vectors here will give a missing transverse momentum. So then you can actually sit down, think about a little bit. Minimum actually obtained when these 2 quantities are equal to each other. Once you know that, this is no longer 2-dimensional minimization. With this constraint, this minimization becomes 1-dimensional minimization. So maybe you can do something useful out of it. And then once you use this constraint and then use this ideal situation, actually this guy becomes this equation here. So Q1 and Q2 are the momentum of the 2 invisible neutrinos. P1, P2 are visible momentum. This is what is known as hyperbola, right? So it turns out in the simplistic case, the mass of the neutrino is, for instance, 0, right? The mass of the neutrino is 0. In the massless case, you can define the major axis, A, here, as the difference between the 2 visible momentum. And then C is what is known as focus, is that right? So this C, distance between the 2 C's, the focus points, will be actually the magnitude of the missing transverse momentum. And then, of course, eccentricity is going to be ratio between the 2. So there is interesting geometrical understanding of these 4 vectors here with this ideal situation. So then what do? I mean, high school physics, right? When you try to minimize something, what do? You take the derivative, and then show there is an extremum, and the show extremum is also minimum. That's exactly what I did with this coordinate system. It's a little complicated because there is a cosine and sine involved, but it's doable. But at the end of the day, solution is extremely simple for the massless case. So it turns out this minimum is obtained when momentum of the one of the neutrino here is equal to negative of the other guy in the visible sector. So Q1 is equal to negative of P2. Q2 is a negative of P1. So P1 and Q1 actually came from same mother. And P2, Q2 actually came from same mother, the other guy, the other W. Actually, they are basically back to back. In that case, the minimum is obtained. However, so now I have a prediction for the momentum of the 2 neutrino, but that doesn't mean the Q1 and Q2 are actually true momentum of the 2 neutrino particles. These guys are just a fake momenta, which happen to minimize this weird quantity. But nevertheless, I don't have to minimize. I don't have to use a computer code to calculate this quantity. I can just calculate this guy because I already minimized. It's not complicated. It took probably 2 weeks or so. But the problem is this sine and cosine trigonometric function. I had to rediscover all the trigonometric identities and to simplify these equations. So I literally took the sum of few Tylenols because I had a literally headache. But then I had to check my solution is correct. So I did a very quick computer simulation to figure out whether my analytical solution is actually equal to the numerical solution using computer code. So at the end here, W pair production, 2 leptons and the 2 missing particles. With this first line, this equation corresponds to the transverse mass in the case of the single production of the W. And the second line actually is almost same as the first line, except that this missing neutrino is replaced with the negative of the other lepton sector. So this is the result. It's extremely simple. Yeah, I decided to delete. It's a little complicated. It's a half page, but it's a little complicated, so I'm not showing this one. So amplitude distribution, it turns out actually looks like this kind of box diagram, and there is a quick drop around the mass of the W, and then this tail is due to the finite width. Because I'm assuming perfect detector here, so there is no resolution. This is purely coming from the offshore effect of the W. But that was a mistake, and then I didn't write a paper, and then I went to the Fermilab in Michigan and Wisconsin. I went a few places to give a seminar. I was very excited about MT2, and then also talk about some spins and couplings, but I was lazy writing down the paper. But some of the senior faculty actually suggested to me that maybe I should contact the authors, because authors repeatedly claim that they were not able to find an analytical solution. But I found an analytical solution. Maybe it was good to communicate with those people. So I thought, oh, maybe that is correct. So I wrote email to Chris Lester and Ellen Barr. Ellen Barr did not respond somehow. But Chris Lester emailed me back, saying that immediately, probably within a couple of hours, immediately saying that, oh, you are wrong. Oh, I had a typo in my email. So it didn't work. But I corrected my typo. And then he said that your solution is very limited, not physical. Why? Because I turned off ISR. So which means that my solution is only valid in extreme case, ideal case. But I didn't write it. But I was busy, right? So both my advisor and I, we were expecting a second baby. He already got second baby. I was expecting second baby. And so I was busy, unfortunately. So we didn't write a paper. But a few months later, they have written a paper acknowledging me. So they did actually a very fairly good job. So back to UK. They actually, instead of using this wrong coordinate system that I actually decided to choose, it worked for me, but it's very complicated because I had to deal with a lot of trigonometric functions to simplify. However, they did actually a great job using Lorentz invariant kinematics in the 1 plus 2 dimensions. So they actually, I'm not going to review, but I'm happy to talk later on. So this is what is known as the momentum conservation in the transverse plane. And then square root S is an analog of 1 plus 3-dimensional Mandelstam mass, total energy of the system. But this is a 1 plus 2-dimensional version. At the end of the day, actually, this is unknown parameter. So they have some constraint, mass constraint. Once again, you don't have to pay attention to what is there. The energy momentum conservation, some of the mass constraint. At the end of the day, this M is the quantity that we like to minimize. And the A, B, C, D, E quantities are written in terms of the measurable quantity. The only unknown is so-called S, Mandelstam S. And then how do you minimize this quantity? Knowing that A, B, C, D, E, all these guys are constant, measurable quantity. The only unknown is S. Take the derivative, right? So the minimum is obtained when S value takes that information. That S is that thing, then this guy becomes the minimum. They did a very nice job, and then their MT2 can be written in this simple form. And if you take the M chi to be 0 here, which is the mass of the neutrino, 0 here and then 0 here, MT2 becomes 2 times AT, assuming the leptons are massless. So AT is actually the quantity that I was showing you earlier. That's exactly the same thing, but they use 1 plus 2-dimensional Lorentz invariant notation, which is actually better. Well, at the end, right, it's the same as this quantity, but it's interesting to be acknowledged for giving them confidence that solution existed. So once you know the solution, you can find it. Actually, Chris Lester later told me that he actually almost gave up because he thought there is no analytical solution. So since then, 2006, like I said, there was a boom here. So most of the papers actually use the idea of MT2 to calculate the mass bounds in some PSM models. But many of the others actually try to develop further, going beyond this simple idea. There is this Korean group, and there is a CERN. And then once again, these guys actually got together. They found something called the kink. This is the mass of the model particle. This is the mass of the trial mass. Normally, this goes like a linear here, parabola shape. But then in some cases here, composite particle, ISR, or some specific case, actually you can kind of see the kind of kink structure. But in practice, this is a very hard thing to measure. And then this UC Davis group actually came up with a great idea how to compute this MT2 minimization in very general case. Actually, still, I believe in certain case, their code is actually fastest code to compute, to minimize this MT2. Still, this is usable. So the list continues. And then Slack group, and then Japan group, and they also use the idea to isolate the ISR against the many different jets. And then once again, this Korean group actually decided to use the same idea to measure spins, because now they know the momentum of the two invisible particles. They can almost, in principle, they can do everything. And then me and my collaborators actually continue to develop in the slightly different directions. And then now our theory postdoc with our collaborator in Pittsburgh, we're actually using the similar techniques to figure out CP angles in the TTH productions. It seems to be working good, so we will see. Hopefully we will finish sometime soon. And then meanwhile, so MT2 has been used in the real data. When I joined the formula in 2006, I believe, 2006 and 2007, it took me 2 years to persuade experimentalists to work on this MT2. I talked to them, but they say they are busy, they don't have enough manpower, and then this looks very strange because you have to minimize over something. They didn't listen. So literally, it took me 2 hours. And then 2 hours of persuading experimentalists, I got 1 citation. But nevertheless, this was actually the first time the MT2 used against the real data. And they used the template method to fit the mass of the top cone in the dilepton channel. And then it works. Right? This was actually very good testing ground. And then now, of course, CMS and Atlas experimentally are very well aware of this one. They further developed the idea. They are using for many of the new physics searches for the background rejection and so on. I think I'm going to skip some of my ideas here. Sorry, let me skip. So this was just the illustration of the how you can develop the MT2 idea in the different directions. And this was also used by CMS to measure the TW neutrino 3 masses simultaneously using some of the kinematic method. So then at some point, Chris Lester, he had this reward. Whoever finds the analytical solution to the MT2 in the presence of the ISR, which I neglected when I tried a few years ago. So I claimed that I found an analytical solution, but he claimed again that is not the true solution because I turned off the ISR. So he was looking for a solution in the presence of the ISR, but there is no solution. It turns out the equation that you need to solve is eighth order polynomial equation. But eighth order polynomial equation becomes quartic equation in terms of x squared if you turn off the ISR. Quartic equation is complicated, but Mathematica solves it for you. So there is a solution. You get 8 solutions. You know which one to pick when you do the numerical simulation. There is only one solution that is consistent with the numerical. So that's how I found the analytical solution. But generally, if you turn on the ISR, the 8th order polynomial equation, I don't know how to solve it. I still believe there should be a solution because there is a numerical solution. Why there is no analytical solution? Unfortunately, I don't know how to find it. Every year, like around Christmas and the January 1st year, I don't know, work on something. Then I always come back to my notes, try to find my mistake where I can simplify the 8th order polynomial equation. I think there might be a way to do this one, but I don't know the answer. So meanwhile, when I was like, what I did was, ISR is always problematic. I want to turn off ISR, but I cannot. I mean, in reality, this is always there. Sometimes we get confused with the ISR, initial state radiation, with our signal. I mean, this is always there. It's always a problematic one. But sometimes useful, but it's always there. Effectively, to turn off the ISR, so what I did here was, this is a missing transverse momentum. Here is the momentum of one of the visible sector. This is the momentum of the other visible sector. This is a PT of the transverse momentum of the ISR, assuming I know how to isolate the ISR. So then what I did is project all the other vectors with respect to this PT, meaning that I can decompose any vector into the parallel part of the PT of the ISR or perpendicular part of the PT, right? So I can actually split this guy into 2 directions, parallel and the perpendicular component against the PT of the ISR. So then if I look at only the perpendicular direction, effectively there is no ISR because I'm projecting twice. Remember, whole transverse quantity idea is we don't have much information about the momentum along the z direction, so we only look at the transverse plane. But then I have another reference direction, which is the direction of the PT, direction of the ISR. But then I'm going to define another transverse plane, which is orthogonal to the PT of the ISR. If I play this same game on that plane, second transverse plane, so then effectively there is no ISR. So that's what I call MT2 perp. So I'm running out of the indices here. So T is already used, so I use the perp here. But then here I can use all the analytical formula because there is no ISR effectively here. But then Chris says I cheated because I cannot turn it off because I don't know how to find the solution in the presence of ISR. So I kind of cheated. Then actually that's the time when he actually removed the bet. He had actually 200 pounds. Whoever finds the solution of the MT2 in the presence of ISR, secretly he took out that thing somehow. So then there are many other interesting ideas happening everywhere. I'm not right. There is a more list in here, but I don't remember everything. But here there is a lot of interesting ideas happening for past 5 to 10 years or so. And then one of the interesting ideas is a Rayleigh variable. So our new addition to our department, Professor Rogan. Hopefully he can tell us more about this interesting ideas maybe at some point. So why are there so many variables? So all these guys kind of got together asking why there are so many variables, right? So I think Ellen Barr actually quoted that one over here. Because whoever invents a new variable should be punished because there are so many variables already available. So basically the question is, why are there so many variables? What is the underlying principle behind everything? Actually, this study actually was started from 2009, 2010. It took almost 3 years to finish because we were mainly writing through the emails. One email every week, one email every month. It took us almost 3 years to settle down in the notation and everything. So I always wanted to say I work on M theory. So this was actually a perfect time to say M theory, right? Here M stands for mass. It was very difficult to persuade the Ellen Barr and Chris Lester not to put this as a title in the paper because it looks bad, right? If you write this one. So it took some time but instead they claimed that we should have the picture of a squirrel, and which editor rejected. And then we said that, well, if we are not allowed to have a picture of this flying squirrel in the paper, the first page, we are going to withdraw. And editor said, fine, okay, do whatever you want. And then instead, the editor asked us to change the title to something else. So in that study, what we did was we systematically analyzed how to compute transverse quantities. It's not like you are just dropping the z component. When you find the transverse momentum, that is what we do. However, the question is what you do with the energy component once you drop the z component. So there is a little bit subtlety when you define the transverse quantities. So we found actually at least there are 3 ways to do this thing in the literature, even in the computer code. And the languages are like kind of a mixed. Some people call it transverse mass, but actually they meant the transverse energy. Some people kind of use the different names and different notations. And then once you project transverse quantities, the question is how do you combine them? Do you combine the momentum of the two first and then project? Or do you project first or do you combine them later? Surprisingly, they don't commute. They commute the XY component, but the energy component is always problematic. And then how do we categorize the reconstructed object? How do we define the most general mass bounds variables and so on? At the end of the day, what we found was that many of the existing variables actually can be combined in the unified fashion, and that we call them mass bound variables. But this has been around for a few years now, but similar techniques and ideas still being used. But I'm not going to go through it, but many of these variables that was proposed in the past 5 to 10 years or so, once again, they can be rewritten under the same guiding principle. One of the interesting is, I know experimenters like to use HT and M effective, some quantity called M effective and HT. I never thought actually this can be derivable. You can actually derive that quantity by minimizing this one. But unfortunately, most of the time, people include the ISR as a part of the M effective. That's why there was no clear derivation of the M effective. But you can actually systematically derive HT or M effective by doing exactly the same procedure. Anyway, so at the end of this study, what we could claim was that actually the mass measurement, a lot of people get confused because whenever I talk about the masses, people always say I'm doing precision measurements, the mass measurement. But actually that is completely wrong. Mass measurements actually stand for parameter estimation and discovery techniques. That's what should have been called. but we still call the mass measurement method, although we are not actually measuring the mass only. We can do a lot of different things, of course, mass measurements, and then spins and couplings, and also same technique can be used to suppress the backgrounds. And then that also allows, sometimes, depending on topology, allows a reconstruction of the full system, including the missing particles. And then this kind of idea actually serves as a basic guidelines to understand the kinematics and the event topologies. So for next 5 minutes or so, I'm going to give you one example that I used to understand one of the interesting excess that you might remember here. So we mentioned something about resonance, right? So resonance signal gives a bump in the invariant mass distributions when you put all the decay product together. But then location of the peak in the invariant mass is interpreted as a mass of the resonant decaying particle. Well, that's what we said. So resonance gives this bump. But then you can ask, does bump means always resonance? Going this way, probably okay, but going backward is also non-trivial question. So what we were asking was, is a non-resonance interpretation of the resonance signal, is it possible? Actually, it is possible given finite statistics. So probably many of you might remember, yes, 750 GeV. Oh, yes. This was, okay, I don't have to give you all the history, but this was some fairly large excess in this tail, around the 750 GeV. As far as I understand, almost everyone was trying to fit the data with the resonance. But when I saw this one, oh, why not that, right? So the question is, can you actually fit the data with this shape, the kinematic endpoints? Answer is yes. So the common features of this kind of invariant mass or kinematic endpoints, usually shape looks like that. It doesn't have to be linear, but it rises this way. It falls down relatively rapidly. There is a kinematic endpoint that I call E, and there is a location of peak, P. So usually this kinematic endpoints over here, this guy is close, sorry, the location of the peak is close to the endpoints. So then, since this guy is close to the kinematic endpoints, when you have a low statistics, you might have a more event near this peak and then less over here. And then this is good because that's where precisely where you have a large backgrounds. So when you see some kind of excess, you are likely to see the something over here first and then this part later. So this part is actually buried under the standard model background. So we did a quick exercise. We actually consider many different topologies, but best one is actually this so-called Antidote topology. So A particle decays into B1 and B2, and then B1 and B2, each one decays into 2 photon and some particle. Let's say this is an invisible particle, carry out some momentum. But then I know some of you might remember this was a 2-photon system. There was a very little amount of the missing transverse momentum observed. But then surprisingly, when you try to maximize the invariant mass out of this system, you actually naturally minimize the amount of missing ET. So that there is an anti-correlation between the invariant mass of the 2-photon system and then PT of the 2-photon, meaning that PT of the 2-photon system is the same as the transverse momentum of the 2 invisible guys. So if you select only the event near the endpoints over here, around the 750 GeV, 800 GeV, the amount of the missing terrestrial momentum you will observe after the cut will be actually small. So therefore, when you actually focus on this area, actually there is a very little amount of missing energy. But this is not actually completely new. If you actually work on kinematics, this kind of anti-correlation is very well known. But surprisingly, this one actually fits very nicely with this happening 750 GeV excess. And then this analytical expression is actually already derived for the invariant mass of the 2-photon system for this particular topology. So with my collaborator, we did actually very quick fitting and then show that actually fit is actually fairly good. And we did some numerical study, and then it was consistent with actually our analytical fit. So kinematic idea actually will sometimes give you some interesting directions too. So then we used actually phase space, so-called phase space decay, to fit the data. But if you have a non-trivial spin and couplings, so generally in the invariant mass distribution, but this is analytical expression, you get extra terms here. So by playing with the couplings and spins, you can even make it actually even closer to the resonance structure, but which I haven't done. So name of the game here is the LHC. So game is, once again, taking lots of pictures for next 10, 20 years or so. So we'd like to add more terms in this Lagrangian. That's the goal. So how do we do it? We will have to see. Of course, here the particle, there was not 750 GeV. At least that gives us some idea what could be happening in this next LHC run for next 10, 20 years. So that was up to some minor issues. That was already consistent with the previous data, previous collider data with from the earlier colliders and precision data and so on. So this is actually kind of a good example, which might show up for next LHC run. But then this first discovery of new physics, and then following up the exploration, subsequent exploration can be achieved, of course, by equilibrating the latest ideas and experimental developments. So we are going to usually focus over here, what we call phenomenology. And then, of course, we have to try to eliminate the blind spots and then make this thing bigger. And then I strongly believe that actually this is where the kinematics actually plays a very crucial role in understanding this event topology that we'd like to study. I think I'm going to stop here. And when I was working on the slide last night, somehow I accidentally found that this is some of the old jokes. I didn't make all of them, but I modified a little bit. But if you recognize some of these things, probably you must be old enough to recognize some of these jokes. So let me stop here, and if you have any questions, let me know.
Any questions for Casey? You did a great job of keeping me awake.
You mentioned the fact that if there is a numerical solution, there should be an analytical solution.
That's my belief. No, that's my belief.
Where does it come from?
No, that's my belief. Like I said, yeah, there might be no analytical solution, true. But then when you take the ISR going to a certain limit, there is a solution. So why am I not able to find, full solution?
Because it doesn't exist?
Well, maybe it doesn't exist. Yeah, like I said, I don't know the answer. I get some equation in a closed form, but I'm not able to find a solution explicitly. The best thing is I write down some kind of a relationship in a closed form. So I don't know. So if somebody finds the answer, I think I'm going to try PLL. I don't think I can try nature, but I can try PLL. Any other questions, comments?
Is there any ongoing analysis on finding a kink structure at the LHC?
I'm not sure about kink. I also worked on the kink a little bit, but practically, as you know, it's very hard to see, and it requires a lot of statistics. And then if you are going to measure a kink, probably you might be able to measure something else first before actually you measure the kink. It's an interesting idea, but I'm not sure whether it's practically useful. That I'm not sure. Yeah, I don't know the answer.
Thank you again. Thank you.